Welcome to the first lecture for Chapter 7 of Living Physical Geography by Bruce Gervais, The Changing Climate. In this lecture, we're going to go over how, and in fact, this whole chapter, we're going to go over how scientists study climate, how we investigate past climates, and how we think about future climate. How do we go about predicting what we think is going to happen to the climate system in the future? We'll also consider the idea of anthropogenic or human-caused climate change, how human activity has changed the atmosphere over time, how that is impacting climate, and how those changes will in turn affect us, as humans are very much dependent upon the climate we exist in. We are going to kick things off with a quick example of how climate change can impact human society and activities by going back in time to the Greenland Norse society. If you know anything about Greenland today, you know it is the world's largest island that is about 80% covered with solid ice. We're talking an ice sheet 3 times the size of Texas. Very cold, very icy. It was not always so. During a period of natural warming, called the medieval warm period, that occurred from about 950 to 1250 AD, or CE if you prefer, this dude called Eric the Red, who was a Norwegian living for various reasons in Iceland at the time, convinced some of the Icelanders that it would be a really good idea to set up a colony on Greenland because the climate was fairly warm at the time. It was conducive to farming and growing livestock, so that's what they did. All these colonists went out to Greenland. They set up farms. They grew things, they raised livestock. There was also quite a thriving ivory trade between Greenland and the rest of Europe because there were a lot of walruses around, so they would hunt these walruses for the ivory in their tusks and trade with Europe. And things were going swimmingly. They had quite a nice little society going there. And then, right around 1350 CE, a natural period of cooling occurred called the Little Ice Age. This cooling made sea ice more prevalent, which made traveling and trade to Europe quite a bit more difficult. It ended up becoming way too cold for them to grow any food or to raise livestock, and it turned into a little bit of a starvation scenario, we think. So these settlements were, although they had been thriving at one time, were just abandoned. The last actual written record we have of the Icelandic North in Greenland is from the 1500s. This is an example of how a shifting climate will shape human destiny by forcing us to do certain things. The picture you're looking at here is a picture of an abandoned Greenland church that was set up by those Iceland, Norwegian Greenland colonists. This still exists on the southeast coast of Greenland. This is one of the very last remaining physical pieces of evidence that we have that the Greenland Norse society actually existed. So we're going to start off by considering a broad scale view of the climate system overall. 2 words you should be very familiar with by now, I would hope, and to know the difference between are weather and climate. Weather is what you get when you look out the window, and climate is what that weather looks like out the window over a 30-year period. Climate is a long-term average of your weather, whether it's temperature, precipitation, wind, humidity, whatever, plus how often, or the frequency of how often, extreme weather events like severe droughts or heavy rainstorms, things of that nature, how often these occur. All of those things represent the climate of a given region. Weather, on the other hand, is if it's thunderstorming or cloudy outside. Weather is just the state of the atmosphere at any given moment. Climate is the state of the atmosphere over a very long extended period of time. When we're talking about climate, we are generally talking a temporal period of 30 years or longer. So this table gives an example of both weather and climate, along with the temporal scale as far as how long they last and what that particular phenomenon actually is. So for example, a sea breeze or cloudy conditions might last just a few hours. A hurricane could last a week or two, but all of those examples are still just weather. Now, something like hurricane season or the Asian monsoon, which is that monthly, annual, massive seasonal time switch, or something like the El Nino Southern Oscillation, these have to do with climate. These are climate phenomenons, and they occur over the period of a much longer time. Here's a climate graph again. You should be familiar with climate graphs by now. We've seen these a few times. We've seen them to look at temperature at different locations, but now we're going to add something new. We are adding in precipitation. You are going to see a whole lot of climate graphs in this next chapter, Chapter 8, the chapter on climate biomes. So it's best to just get really comfortable with them. Let's kind of revisit this. Remind yourself that along the x-axis, we have the months of the year from January through December. And on one y-axis, that vertical axis, you have temperature represented in Celsius or Fahrenheit degrees. Usually you see both. One will be in parentheses. Now we have another opposing y-axis. This other vertical axis is talking about centimeters of precipitation. So we show precipitation on the climate graph, in these blue bars that you see down towards the bottom of the climate graph. And of course, that temperature is that red line. We have two different locations we're looking at here. San Diego at 34 degrees north latitude and Tucson at 32 degrees north latitude. Basically very similar latitudes. However, you'll see some differences here. They do have similar precipitation patterns. They tend to get most of their precipitation in winter and very, very little in summer. I will totally acknowledge, though, that Tucson has these two spikes in July and August. That is from something, they have their own monsoon. It's the North American monsoon. And I don't know if we'll get into that or not, but it's an interesting phenomenon. But overall, the precipitation patterns are fairly similar between these two cities. However, look at the difference in temperatures. There is a much greater temperature range between summer and winter in Tucson as opposed to San Diego. That's because San Diego is a coastal city. It has that maritime influence. And Tucson is basically in a high desert plateau, much further inland, so it gets a much larger temperature range. These two climate graphs give a good representation of how we think about climate in a given location. And the nice thing about climate graphs is that they allow scientists to compare locations or compare the climate at different locations over time. They allow us to see how one location's climate is different from another, and usually we already learned that that can tell us a lot about how that particular location is situated. Is it inland? Is it coastal? Is it high elevation? Is it low elevation? Well, if we look at these over a long period of time for a given location, say a city or a region, your backyard, pick a location. If we look at these over about 30 years, year to year to year, we can actually see how that climate system might be changing over time. That is something called a trend. So let's also remind ourselves of the parts of the climate system and how that all works. So the climate system, or the climate, results from interactions between the atmosphere, the biosphere, the lithosphere, the hydrosphere, and the cryosphere, which is that frozen portion of the hydrosphere. Energy and matter move through these systems, and they ultimately form the overall climate system of a given region. When we talk about current climate change, that we are experiencing right now as a sort of human-caused or anthropogenic event, we're talking about some change in the climate that has been caused due to human influences through human activity. It is not something that would have necessarily happened on its own in nature at the rate that it is occurring now. So naturally, the climate has changed many, many times without any human influence in the past. We are a fairly recent development. We consider these changes part of natural climate change, things that are just going to happen whether we are here or not. Since about 1880, however, the planet has begun to warm up at a really unprecedented rate. And whenever the long-term average of something, precipitation or temperature or whatever changes, that's when we consider it a climate change, whether that be due to humans or something that would just happen naturally on its own. We can't blame one individual event, say like a Hurricane Katrina or Harvey or Laura, on something like climate change. But if every hurricane that starts to happen happens to look a little bit more like a massive, devastating high category hurricane like Hurricane Katrina or Harvey, and a little bit less like a weak thunderstorm, well, then we might be able to say that hurricane climate is changing, or rather that the ultimate climate is changing hurricanes. So let's talk a little bit about how this happens. We need to think about two things here, climate forcing and climate feedbacks. We've mentioned feedbacks a couple of times. So let's go into detail here. A climate forcing factor is something that forces the climate, causes the climate to respond in a certain way, but that thing itself is unaffected by the climate system. So think about this for a minute. We have something called a solar forcing. This is a good example. A solar forcing is something that changes in the sun that causes less solar radiation or more solar radiation to be output than is normally the case. And that change in the sun's output changes our climate, but the change in our climate does nothing to the sun. The sun just goes on its merry way doing its thing, completely oblivious to us. We didn't do anything to that actual sun, but it is most definitely doing something to us. A volcanic eruption, we'll call it a volcanic forcing, is similar. The climate does not change the volcano, but that volcano erupting can definitely change the climate. When volcanoes erupt, they throw out a lot of ash and sulfuric acid and all kinds of nasty particulate matter out into the atmosphere, specifically up in the stratosphere. A whole lot of stuff going up into that stratosphere, and that tends to be very reflective, and it bounces a lot of the incoming shortwave radiation back out to space, so that never gets to the Earth's surface. This can cause short-term cooling by blocking out that solar radiation. We would consider that a volcanic forcing. So these are both forcings. They force the climate to behave a certain way. Feedback is what actually happens afterwards. Does it enhance or diminish climate change that's already been set in motion? We're going to talk about something called the ice albedo feedback in detail right now, because this is a really, really good example that's pretty easy to understand. Specifically, we're going to look at the ice albedo process at work in the Arctic, because this is the place where we are seeing the climate change faster than anywhere else on the planet. We're going to talk about why that is in a little bit, but for right now, let's just focus on the process. Recall that albedo is a measure of the reflectivity of a surface. Lighter colored, smoother surfaces tend to reflect a lot more. That solar radiation is reflected back out to space, and these surfaces tend to be cooler. And then darker surfaces and also rougher tend to absorb a lot more incoming solar radiation, so these will be warmer. Also recall that snow and ice, especially fresh snow or ice, are our highest reflectivity, highest albedo surfaces on the face of the planet. So the ice albedo process in the Arctic is a positive feedback, and it's destabilizing the climate system. Take a look at the first box on the bottom on your left, and you see how warming of the climate melts more snow and ice, that nice high reflectivity surface. As this happens, you are then taking what was very reflective surface and you are turning it into dark ocean. This then absorbs more sunlight, converts it to heat, this melts more ice, and then you go back to number one, and this process just continually moves in the same direction of melting, revealing more dark surface, absorbing more more incoming solar radiation, warming, melting more snow and ice. You get it. Increased cooling could also be a positive feedback. Think about how this might work. So if the climate suddenly becomes much cooler, it can form more snow and ice. And if it forms more snow and ice, then you'll end up reflecting more sunlight back out to space, causing the surface to cool off more and causing more snow and ice to form. You go back to number one. In this case, you're moving everything in the same direction. It's just feeding on itself. With a negative feedback, something has occurred in the climate system to move it towards a certain state, but then this counteracts changes in that climate system, helping to stabilize temperatures by reducing the effects of warming or cooling. So for instance, say you have warming occurring at the Arctic and it's melting sea ice. So we're getting that more exposed dark surface, and it starts to warm enough that it evaporates more water into the atmosphere, creating clouds. If this were to happen, what if that cloud feedback system then kicked in because we are reflecting more incoming solar radiation back out to space? It's not continuing to warm the ocean. In this instance, it's going to cool things down. And eventually that's going to lead to more clouds, and it's going to lead to less incoming radiation, and it's going to lead to the reformation of snow and ice. So these are a whole bunch of different ways that we can change the climate in one direction or another. It's kind of confusing, but I just want you to be exposed to these ideas of forcings and feedbacks. Now we're going to shift gears slightly and talk a little bit about trends, cycles, and anomalies. An anomaly is a weird event that just happens. It's kind of a one-off event that we do not expect. It just pops up out of nowhere. Then we'll also talk about different cycles that go through the climate system and that change our climate system, and some trends that we are currently seeing. We have three natural modes of climate change. Natural modes: a long-term trend, a repeating cycle, and a random anomaly, that weird event and unexpected thing like, say, a volcano exploding. All of these changes are forced by different climate forcing factors, and they in turn force climate feedbacks, and those feedbacks push our climate in a certain direction. So let's talk about each one of these a little bit, kind of give you an idea. We are going to start out with a really, really long time ago and talk about the first major climate shift that we are aware of. It is known as the Cenozoic cooling trend. This occurred about 55 million years ago. 55 million years ago, the Earth's average temperature was about 12 degrees Celsius or 22 degrees Fahrenheit warmer than it is right now today. We had no ice at either pole, and our atmospheric carbon dioxide concentrations were above 1,000 parts per million. That's what that ppm stands for. They're at roughly 400 ppm today. And we'll talk about how we know or think we know that CO2 concentrations were what they were like 55 million years ago in just a minute. But meanwhile, let's just be aware that we have some insight into thinking that it was much, much hotter back then. Right in our records, that we have, we see that a massive cooling event happened starting about 55 million years ago, and we think it's because of the building of the Himalayas and the Tibetan Plateau. In this graph you are looking at from your book, this is showing you over time how this happened. What we're looking at here is on your y-axis on the left, we are looking at temperature anomalies, not actual temperature, but an anomaly defined as how that temperature was different from our temperatures today. We are using today's temperatures as that 0 degrees Celsius, and then we are showing change as we move back in time. Your x-axis is showing you the time in millions of years before the present. 0 is what we are considering the present right now, and we're going back a little more than 60 million years. So if you look at this graph, you will see that as the Indian subcontinent crashed into Eurasia, causing the formation of the Himalayas and the Tibetan Plateau, that's what geologists believe caused this whole formation of it in the first place. All those massive mountains in that mountain change, it changed all of the airflow on our planet. Consider that for millions of years, prior to 55 millions of years ago, there had not been a mountain chain there, and the airflow had run in a certain way, unimpeded, up into and around the planet. All of a sudden, and I'm saying all of a sudden geologically, so all of a sudden is like over millions of years, but all of a sudden we have a huge mountain chain that then forces this airflow that had not encountered a mountain before to now be forced upward. It is forced upward, it cools and it condenses and it starts making rain where previously it had never made rain before. This is going to change everything downwind from that location climate-wise. All of a sudden we have things going on that had never happened before, and we believe this is what caused that massive cooling trend all of a sudden starting right around 55 million years ago in that location. This cooled off the planet considerably. Then about 35 million years ago, it got cold enough that it started to build Antarctica as far as the glaciers are considered, and then we started building northern hemisphere ice sheets about 1 million years ago. Our temperature has risen and fallen a lot through time. Now let's fast forward in a geologic timescale sense to the last 2.6 million years. This is something we call the Quaternary period. During the Quaternary period, the last 2.6 million years, the climate has cycled between cold glacial periods, where glaciers are being formed, and warm interglacial periods, 22 different times. Glacials last about 90,000 years, and then they are followed by a warm interglacial that lasts about 10,000 years. We are currently in an interglacial period called the Holocene. The Holocene has had an unusually stable climate that started about 10,000 years ago. This time series graph from your book shows quaternary temperature cycles. About 2.6 million years ago, there is a noticeable difference in the temperatures that marks the beginning of the quaternary period. Climate swings occurred on about a 41,000 year cycle before about 1 million years ago, and then transitioned to a 100,000 year cycle after that. There's also a 23 to 24,000 year cycle that's not highlighted in here, but it occurs within those other two cycles. These are something called Milankovitch cycles. Milankovitch was a Serbian mathematician and astronomer, climatologist, geophysicist, all around smart guy, who started to look back at some of the records that we had and was able to identify some recurring temporal patterns, some cycles that
occurred within these that helped explain what was going on temperature-wise. We have 3 different cycles that occur due to the variation in our relationship with the sun. These are very small changes on a universal scale, very small changes in our orbital geometry that ultimately lead to these different glacial and interglacial cycles. This is what we call orbital forcing. Remember, I'd already mentioned solar forcing and volcanic forcing. Well, this is another really large forcing mechanism over very long time scales called orbital forcing. Here are the 3 examples of our 3 Milankovitch cycles. We have first orbital eccentricity, then we have the Earth's tilt, and then we have something called precession. So with orbital eccentricity, this is a 100,000-year cycle. This is where the orbital cycle around the sun actually changes shape. It goes from more circular to more elliptical, and it can change by about 18 million kilometers. Then we also have the tilt of our planet. Our current tilt is about, that axial tilt is about 23.5 degrees. But this can vary from between 21.5 to 24.5 degrees. And it can do this over periods of about 41,000 years. We also have something called precession. Precession is wobble, really. If you've ever spun a top or a dreidel, or you've done one of those things where you spin a penny or a nickel on a table, you watch it spin and it does this nice straight up perpendicular to the surface you have it on spin, but then it starts to wobble after time. The same thing happens with our planet. As it's spinning on its axis, it will every now and then start to wobble a little bit on that as that axis is tilting and spinning at the same time. This happens over a period of about 23 to 24,000 years, and this causes the timing of the seasons to change. I would like you to go through this and read through the graph carefully just to kind of familiarize yourself with what's going on here. These cycles are massively long, and at a temporal scale, that means that over our lifespan, they're not going to change. They won't change over 10 generations. We will not see these changes, but it's an important thing when you're all thinking about overall climate change over a really long time. They do make differences, huge differences in the climate. So now let's look at an anomaly. An anomaly is any random occurrence that happens, and an example is, say, a change in the sun's output, or changes in our ocean circulation, or something like a volcanic eruption. Our sun runs through cycles of sunspots. You've probably seen pictures of these where they've taken pictures of the sun and you'll see little random dark spots here and there on the sun. These are changes in the output of the sun. Typically, when you have more sunspots, that's indicating a lot more radiation coming off the sun, and fewer sunspots is less radiation being emitted. We think that the little ice age that abruptly changed the Greenland Norse Society's living location was due to low sunspot activity. The sun just got a little weaker, and it triggered the little ice age. We also think that the medieval warm period that actually got them living there in the first place was there because the sunspot activity was unusually active. These are caused by climate forcings, and these then have cause feedbacks that are different from those that drive longer-term climate patterns. Here's another anomalous climate event. This is a picture of the exploding Mount Pinatubo in the Philippines when it erupted in the early 1990s, 1991, I believe. Volcanoes have the capacity to promote short-term cooling because they block out solar radiation when they erupt. You can find pictures of this eruption and videos on YouTube that are pretty impressive. You should look it up. The eruption of Pinatubo, that is hard to say, ended up creating a midnight type of scene at noon just because it blocked out so much of that sunlight. It was massive. And it did, in fact, have a cooling effect on the climate for, I believe, like a year and a half afterwards. Still, we were seeing impacts of this. We can also look back at a much older anomalous event, something called the Younger Dryas. This was a period of cold temperatures across most of the northern hemisphere that happened about 12 to 13,000 years ago. We think this happened because of a massive upset to the oceanic circulation. Remember back in chapter 10, we talked about the thermohaline ocean conveyor belt, that oceanic circulation that is driven by salinity and temperature differences. Well, about 13,000 years ago, we had this thing called the Laurentide ice sheet. The Laurentide ice sheet was this massive sheet of ice, we're estimating up to like 2 miles thick in some places, that existed over a lot of North America about 13,000 years ago. What we believe happened was that something caused that Laurentide ice sheet to start melting, occasionally in very quick bursts of massive outputs of fresh water flowing across North America and then into the Atlantic Ocean. We're talking huge amounts of fresh water. So much so that it disrupted the salinity levels in the Atlantic Ocean. And remember, that's what's driving the circulation there. As that salinity became less and less saline, there was less and less circulation going on, and it just pretty much shut down. And when it did that, it was not moving things around to help warm the planet in that area. So here's a graph showing what the temperature looked like about 15,000 years before present. So things are, kind of warm. We got a nice warm spike there going right around 15,000 years ago, and then all of a sudden it just tanks. We think this was the Younger Dryas event. And then at some point, everything started to stabilize, and it warmed the temperature of the planet, at least in North America, up quite a bit, and it has remained fairly stable for about the past 10,000 years. So here's a graphic of that ocean conveyor belt, that thermohaline conveyor belt, just to jog your memory. And you need to pay attention to what's in these boxes. Remember that it is very much dependent on a balance between that temperature and salt. The thermohaline conveyor belt sinks in the North Atlantic due to the incredibly cold temperatures and the very high salinity of the water. If you change that dynamic, it has the ability to turn this entire system off. And if that happens, you no longer have that warm ocean water from the tropics being moved towards the higher latitudes to help warm them up. So we do believe that when this ice sheet melted, it really upset that balance of fresh water and temperature in the North Atlantic. Shut down the conveyor belt, stopped the heat transfer, ultimately cooled us off. So if you look at these boxes, 1, 2, and 3 describe the general conditions that I'm describing and how it works. Here we have a map of what we believe the Laurentide ice sheet looked like and how much area it actually covered. Now, if you imagine, if you have an ice sheet that's 2 miles thick over an area this large, once it starts melting, you're going to have a whole bunch of fresh water runoff. We believe that as it melted in response to some of those Milankovitch forcings, that meltwater flowed out the St. Lawrence River, the Mississippi River, and the Mackenzie River, added that fresh water ocean to the oceans into which it flowed and disrupted those salinity levels. At times during the melting process, we would have melting and then refreezing, melting and refreezing, causing ice dams to form.
which in turn would create these huge inland lakes, such as we have a few shown here, like Lake Agassiz and Lake Algonquin. Scientists hypothesize that these ice dams broke repeatedly over time and released massive pulses of fresh water into the North Atlantic Ocean. These pulses then slowed or stopped the ocean conveyor belt system and caused cooling events such as this Younger Dryas. It's important that you remember we were not there while this happened. And so you might be wondering to yourself, well, how do we actually come up with these old temperature records? And bear in mind that this is our best guess. Science is built by people hypothesizing how they think something happened, and we reach our best conclusion about that how that happened, and then we present that, and people think this is like the hardcore truth. But realize that ideas of how things have happened and changed do change over time. So this is our best guess. We could be wrong, but for right now, based on the evidence we see, this is what we believed happened. How do we come up with these conclusions? Well, we start with paleoclimatology. A paleoclimatologist is someone who reconstructs Earth's past climates. This is how we come up with old temperature records when we were obviously not there to record the temperature ourselves. Temperatures are the easiest things to record in natural materials like tree rings, glaciers, cave deposits, even ocean sediments. These are materials that we can use to tell us about past climates. These types of materials are known as proxy records. They are a proxy for what we believe occurred based on what we see in these different materials. You might have, as a small child, learned about things like tree rings growing every year, glacial deposits, and coral and clamshells and all kinds of things also put on yearly, or we say annual, layers. As they grow, a new layer is added. If we take something like tree rings and we take using different types of instrumentation, we can learn about that tree's chemistry and the environment that it was growing in while it was alive over a period of years. And if we put that together, that tells us a lot about the type of temperature it existed in, as well as, in some instances, the type of precipitation that it was in. And this way, we can help use this to reconstruct past climates. So we're looking at these things here like glaciers and coral reefs that all have these annual growth bands that develop as they grow each year for different reasons. In addition, we can pull our very oldest records from the very bottom of the ocean with marine sediment cores. What you're looking at here, we have this very cool glacier on your upper left. I can never pronounce this glacier. It starts with a Q. It's in the Andes in Peru, I believe. On your right, we have a young lady working on ocean sediment cores. These are long tubes of basically mud extracted from the bottom of the ocean that we can then cut up, open, and look into and see what type of substrate we're working with then, which tells us a lot about what the climate was like and what type of organisms were living in it. Now, if you think about this, this is formed in layers because there is always stuff settling down to the bottom of the ocean, and it builds on itself year after year after year, more stuff coming down, and it forms these layers. We can cut into and look and see how the conditions changed over time. At the very bottom of the slide, we have a drilling rig. This is one of those ships that goes out fitted with a drilling rig. They drill down into the ocean, suck out these cores, and then we can cut them up and look at them. I have worked with these. They are very stinky, but they're really fun to dig through and look at the different things you can find that happened vastly long times ago. One proxy that is not shown here is coral reefs. We can take corals, take cores of those, go into the laboratory,
drill out some powder from that coral, and look at the geochemistry of what that coral is made up of to tell us a lot about temperature and a lot of times also about precipitation that was happening in the area where that coral grew. Corals typically live a really long time, so they provide a nice long record, usually only about a couple centuries at the oldest, but still a nice record that we can really get a lot of information from. I have also worked on a project where there were sediment cores taken from Yosemite National Park, just some of the meadows in there. And my job was to dig through those sediment cores and sediment samples and look for pieces of charcoal over time that had occurred in the different layers. We would go through layer by layer by layer, successively lower and lower, further back in time, and count the number of pieces of charcoal and note the size and the other types of things that were in that soil that we had pulled out, to reconstruct like past Native American fire use and then natural forest fires that had occurred in Yosemite National Park over a really long time. I think we were able to get back about 3,000 years. Looking at trying to find charcoal pieces, looking through a microscope for hours and hours and hours on end is really tedious. And that was the point at which I totally decided paleoclimate was not for me. Nonetheless, paleoclimate can tell us a lot about what happened in past environments. One of the ways that, and this is an answer to how do we know what happened this long ago? Picture a little of how we can look at air bubbles in ice. If we core ice out of an ice glacier, scientists can tap into the air that was frozen into little pockets of air bubbles all those years ago. And from that air, they can then reconstruct temperatures based on the types of gases that we see in that ancient air that we have caught. And we compare that to the gases we have today, and we can from this kind of extrapolate what the temperature differences were based on the different percentages of gases that are caught in those air bubbles. It's pretty impressive what climatologists can do. And that is it for this lecture. Next up, we are going to look at carbon's role in the climate system. We will compare naturally occurring long-term and short-term carbon cycles and discuss the role of human activity in altering those natural cycles. See you next time.